Okay, let's start with graphing y equals x squared. Boom. So this is the graph of y equals x squared. Put a point on there. Beautiful. Nice happy point on a nice happy graph. Okay. How many zeros does a degree 2 polynomial function have? Definitely 2. When you look at this picture, what can you tell me about those two? They're both real, and what are they? 0 and the number 0 again. We call that a repeated 0. Sometimes when describing repeated zeros, you might say that is a 0 of multiplicity 2. It's repeated twice. Okay? Let's compare that to another even power, x to the 4th. So you can see the differences. X to the 4th is a lot more flat, because what happens to numbers that are between 0 and 1 when you raise them to a fairly large power? They get even smaller. Okay? So numbers that are already close to 0 to begin with get even closer. So you get this really flat-looking bottom to it, but the minute you start plugging numbers larger than 1 in, they explode huge. So you have this flat bottom, but then it curls rather quickly to some really, really steep end behavior, right? How many zeros does x to the 4th have? 4. Can you tell by looking at this picture how many are real, how many are imaginary? Realistically, no. Okay? I can make an assumption that this thing has roots at 0, and because it touches 0 and bounces away, those roots are definitely repeated, correct? But how do I know it's not repeated twice? Because doesn't repeated twice also touch and bounce away? Yes, but it's not true. Okay? The only way you know for sure is by factoring the equation and actually solving it. X to the 4th is x times x times x times x. Each one of those factors has 0 as one of its zeros. Now, when you see something that's that flat, can you make the assumption it's probably repeated more than twice? Yeah. Are we done smelling each other? Okay. Here's what x to the 6th looks like. You can see it even flatter still at the bottom. Okay? But the reality is it is completely rounded and it only touches the x-axis at 0 and that's it. Let's compare that to an odd degree. How about x to the 5th? Okay? The difference between a 0 that's repeated an even number of times as compared to an odd number of times is what? The odd number of times actually does cross through the x-axis, right? To the left of 0 is below the x-axis, but to the right it's above. So it actually is crossing through. But the same thing is true. As you approach that x-intercept, the curve bends itself so that it becomes parallel to the x-axis for a tiny instant, right? Crosses through the x-axis and then it starts curving upwards at the end. Okay? So you're starting to get a feel for what these look like in the repeated multiplicities. Let's create a graph. Let's do y equals, where would you like this graph to have an x-intercept? Let's keep the numbers relatively reasonable. I heard 5. So x minus 5. And I'm not going to repeat that 0. That's just going to be once. Okay? Where else would you like to have an x-intercept? So let's do x minus 2. Would you like that one to be repeated or not? Yeah, how many times? I heard 3 times. Where else would you like this thing to have an x-intercept? -1. Would you like that one to be repeated? How many times? 4. Okay, so we hit enter. This is what we get. Let's make this a little bit more reasonable to look at. I'm just going to zoom out vertically. So I'm not squashing the graph, right? I'm just squashing our view of it. So you can see, not only is the graph squashing down, but so are the axes labels. See, now I'm going up 10, 20, 30, but yet on the x's go by large amounts. So I'm just skewing how it looks. Okay? And so that's actually, we're still not seeing all of it, are we? Because there's x-intercept over there. All right. Do this even more. Wow, that dip is really down there. I'm just going to leave it like that. Okay? But that is a dip right there. So we can see the end behavior. To the left, to the right, both sides are going up to infinity. That's a sign that this has what type of degree? Even. And since it's up on both sides, that tells me the leading coefficient is what? Positive. We'll go over that in a little bit more detail today. The curve is approaching the x-axis, but as it gets close, it starts curving, and it runs parallel to it, not perfectly parallel, but close, and eventually touches the x-axis at -1, and then ends up bouncing up. So that is a sign that -1 is a repeated 0, and it is repeated an even number of times. Now, do I know for sure if this is repeated 2 or 4 or 6 or 8 or 10 times? Just by looking at the graph? I really don't. Okay? I would make an assumption that because it gets flat like that, you know, if it was only repeated twice, it would really touch it and bounce away. It would be really rounded. Because it's got some flatness to it, it's probably 4 or 6 or 8 or something like that. So you might guess that it's 4, but you could be wrong. So then it goes up, hits the hill, comes back down. Again, it starts to turn to become parallel to the x-axis, touches the x-axis at 2, but then ends up bending downward. That tells me that 2 is also repeated, and it's repeated an odd number of times. Okay? And it's definitely not 1. You know, it's at least 3 or 5 or 7. Agreed? Probably more like 3. It's pretty rounded. And then 5, it just rips right on through there, so that tells me that that is not a repeated 0 at all. It just shows up once. So if I were to guess, maybe 2, 3, and 1, I might guess that this is a degree 6, even though I think this is actually repeated, what, 4 times? So this is really a degree 8. Okay? Let me create another one for you, and I'm not going to show you what the equation is. I'm going to let you guess by looking at the picture what degree it is. So hopefully I can create a good one here. So let's pause the screen. Okay. Oh my. Alright, so this isn't the prettiest thing in the world, but we'll go with it. Okay. Pretty tricky. So the end behavior is down to the left. This is the end behavior here. Up to the right, that's the end behavior. So there's a hill here that we can't quite see. It's cutting right through at -1. See how this dips below? So it's actually crossing through at 1, turns back up, turns parallel, touches at 2, bounces away, comes up towards 5, turns to run parallel to it, ends up crossing through at 5 and turning up. So somebody look at that and give me a guess for what you think the degree could be. So how many here? 1. So that's 2 total.
3.
Is it crossing through?
Oh no, it's 2 I meant.
So to the left of 2, is the graph above or below the x-axis? It's actually below. And to the right of 2, it's also below.
Oh, but doesn't it go up a little bit? Does it ever cross 0?
No, it's not. It's touching 2 and then bouncing away.
What about it?
So we've got 1, 0 here, 1, 0 here. How many guesses for here? Got to be an even number.
2.
So you want to go 2 or 4?
2.
Let's go with 2.
I'm so confused.
And then how many here?
1, 2.
3. It's turning to go parallel, but then it ends up crossing through, so let's say 3. So if we go 1, 1, 2, and 3, that's 1, 2, 3, 4, 5, 6. So could this be a degree 7? I think it totally could be a degree 7. It's not, but it could be. Do we have enough information just looking at the graph to know for sure? No, we don't. This one, you know, because it gets so flat here, maybe that's repeated root 4 times. Maybe it's repeated 6 times. I actually don't remember. I think I repeated it 6 times. Oh, and that's another thing. You know, maybe this is a root. This is a root. Let's say this one's repeated twice. And let's say this one's repeated 3 times. Does that necessarily mean it's guaranteed to be a degree 7? What about the vertex? No. You can't see imaginary zeros at all. They don't have any effect on the graph. Okay? So yeah, there might be 7 real zeros, but there could be a couple imaginary. Maybe this is a degree 9 and 2 of the zeros are imaginary. Okay? Let's actually look at the equation. Let's get the algebra view up. So there's the equation I typed in. I typed in x plus 1, x minus 1, x minus 2 to the 6th. So 2 is actually repeated 6 total times. And then I did x minus 5 to the 3rd. So this is in fact a 9. That is a degree 11 polynomial. Now, let me just take that polynomial and throw in 2 imaginary zeros to it. I'm going to add the zeros I and negative I. So I'm going to type x squared plus 1. Watch how the graph changes. I'm going to be taking this degree 11 and turning it into a degree 13. Didn't really do a whole lot. Does the graph really look any different besides maybe it stretched down a little bit? Right? It's still crossing at negative 1, 1. It's touching 2 and bouncing away, and it's curving into 5 and then going up. And I added 2 whole new zeros, but neither of them were real. So it didn't really change the way the graph looks hardly at all.
Is x squared like minus 1 equivalent to imaginary?
X squared minus 1? Those are both real. That's x minus 1, x plus. X squared minus 1 is actually these 2 together. I wrote x squared plus 1. The x squared plus 1 equal to 0. You get the square root of negative 1, which is I. And negative 5.
You get that earlier.
Yeah. Keep an ninja straight, Molly. Come on. Okay. Next, let's talk end behavior. Why don't you go ahead and copy paste 4 axes onto your paper? Okay. All polynomial functions have end behavior that falls into one of 4 types. Maybe the graph's right end behavior is up, and the left end behavior is also up. And this is called end behavior, so we don't really care what's happening in the middle. Maybe it's like that. Okay? What types of functions, what can you tell me about the polynomial that represents this if the end behavior is up to the left and the right? It has an even and positive what? Poly? The leading coefficient is even? Alright, there we go. You just told me to shut up?
Not you. I'm just trying to help.
Okay. The degree of the polynomial is even. So think of it, take any even power. If a positive number goes in, what type of number comes out? Positive. If a negative number goes in, it gets raised to an even power. What type of number comes out? So positive inputs, positive outputs, negative inputs, positive outputs. Okay, but that is only true if the leading coefficient is positive, so that none of that gets reversed. So positive leading coefficient. Yeah, we'll just do it like that. Now, polynomials could also be down to the left and down to the right. So positive inputs output negatives, and negative inputs also output negatives. So it's still going to be an even degree, but what can you tell me about the leading coefficient? That will be a negative LC. We could have negative to the left and positive to the right. So positive inputs output positives, negative inputs output negatives. That would be odd degree, but what about the leading coefficient? Positive LC. And then we can have the negative of that, which is up to the left, down to the right, odd degree, negative leading coefficient. So do we all remember that? Okay, this should be very much common sense, because as your inputs get really, really extreme, it's the first term of your polynomial that really takes over and represents the polynomial the most, right? If I have x cubed minus 7x squared, when my inputs become massively large, huge, well, when I cube a huge number, what do I get? An even huger number. When I square a huge number, what do I get? Relatively speaking, a teeny tiny number. If you take a huge number and you cube it and you also square it, relatively speaking, cubing it is going to create a number that is so much massively larger than squaring it that subtracting 7 times that number squared doesn't really do anything. It's almost like subtracting nothing. That's the way it works. So as x gets really, really super huge, it's the x cubed term that really determines what types of outputs it's going to have. And so when you cube a huge number, you get an even huger positive number. That's right end behavior to infinity. Okay.
No, like really.
No, like really, I'm not answering you. All right. So let's do this example here. F of x equals negative x cubed plus 4x. Just by looking at the first term, the degree and the leading coefficient, give me the right hand end behavior and left hand end behavior, and then we want to write it more formally. So what you look at, it's odd, so that tells me that the end behaviors will be different, right? So either up to the right, down to the left, or the opposite of that. The negative leading coefficient essentially tells you what the right end behavior is. Doesn't matter if the polynomial is odd or even. If the leading coefficient is positive, the right end behavior is up. If the leading coefficient is negative, the right end behavior is down. Okay? So, f of x is going to approach negative infinity as x approaches positive infinity. That is the best way to write these. X approaching positive infinity means going forever to the right. F of x approaching negative infinity means going forever down. So as this graph, as you move to the right on this graph, it will plunge down to negative infinity. And then we can say f of x will approach positive infinity as x approaches negative infinity. Okay? So, down to the right, up to the left, looks like this. Right? Okay, I had this genius idea. A video game, an Xbox Connect game, where on the screen flashes a polynomial equation, and you've got to make the gesture to represent it, right? Make millionaires. I'm thinking we call it Dance Your Asymptote Off. Right? Big great name. Or maybe like Graph Revolution or something like that. Graph, no. Not as funny. Who made millions, right? That actually would be pretty good.
Probably like
I can just see, you see that, like, I can just see it at Dave and Buster someday, and you got that guy that never leaves, right? He just plays it over and over and over again. And he's just going nuts, like, he's going crazy. You can even throw, like, inverse functions in. Reflect yourself over that line, y equals x. You can do some cool stuff. I just totally injured myself. All right. How about B? Even degree positive leading coefficient. So f of x is going to approach what to the right? So we're going to say positive infinity as x approaches positive infinity. What's the left-hand end behavior? Also positive infinity as x approaches negative infinity. F of x is y coordinate. So as x approaches negative infinity, that means left-hand end behavior. So it's going up. As x approaches positive infinity, that's right-hand end behavior. So it's up on both sides.
Would that be negative infinity? Oh, you just need to do it. Okay. No question.
There you go.
Sorry.
All right, feeling good about end behavior? All coming back to you? I don't speak German. No, weird. We already talked about this. We've already gone over a lot of this stuff. We've already talked about zeros of multiplicity. So let's do a quick review. The fundamental theorem of algebra. Basically, the fundamental theorem of algebra tells you a degree n polynomial has at most n zeros. And the corollary of that is a degree n polynomial has exactly n zeros. The fundamental theorem of algebra. Okay? We'll review it in more detail in section 2.5. But, so let's suppose we have a polynomial function f and it is degree n. It will have at most n real zeros. It'll have exactly n total zeros, complex zeros. But some of those might be real and the rest might be imaginary. It will have at most n minus 1 tilde dips. Right? We call those relative extrema. That is different than absolute extrema. Because if this is a degree 3, how many relative extrema does this graph have? 2. It has what we call a relative maximum and a relative minimum. That is 2 relative extrema, or extrema.
Could be called local minimum.
Local minimum, local maximum. But what would you tell me about this graph's absolute maximum? It doesn't have one because the graph goes up to infinity. What is the absolute minimum of this graph? It does not have one. Okay, don't say negative infinity. That's like saying, I can't think of an analogy. But they're like, what's the first letter of your name? And you say, purple. I mean, you're saying, what is the highest number in this equation? Infinity. It makes no sense. Infinity is not a number. So I'm asking you a question that has a number as an answer, and you answer it with a concept like, what's the first letter in your name? Love. Or something like that. An idea. Not a thing. No. Okay. These are called relative because it is the technical definition of a relative maximum is, can I create a viewing window where that point is the absolute maximum? Okay? Can I crop this in such a way, including some points to the left and the right, such that that point is the highest? So it is higher than points immediately to its right and its left. That's the definition of a relative maximum. And it's always one less than the degree. Now, does a degree 3 have to have 2 hills and dips? No, I can totally have a degree 3 that looks like this. No hills and dips. It doesn't even flatten out, okay? Is a graph that flattens out like it's going to be a hill and then changes its mind and goes up anyway, is that graph said to have any maximums or minimums? No. In fact, does anybody know the informal word for maximum is a hill? The informal word for a minimum is a trough or dip. Does anybody know the informal word for when a graph turns, flattens out horizontal, and then changes its mind and goes up? We often call those saddles, like on a horse. We often call those saddles. Okay. Here's some stuff. We've already talked about all of this. Let's suppose f is a polynomial function and a is some real number. All of these are true statements. If a is a zero of the function f, then a is a solution of the equation f of x equals 0. Well, duh. X minus a is a factor of the polynomial, and the point a0 is an x-intercept of the graph. Now that is only true if a is what type of number? Real. If a is imaginary, it can still be a 0, it can still be a solution, but it's not going to be an x-intercept, and we don't usually write factors with imaginaries. Right? Okay, good stuff. Let's find all the zeros of this polynomial function. X cubed minus x squared minus 2x. How many zeros does this polynomial have? It has 3. How many of them could be real? All 3 could be real. And therefore, how many are imaginary? None. How many else could be real? Could 2 be real and therefore the other 1 is imaginary? No, that's impossible. Because imaginaries always come in what we call conjugate pairs. If 3 plus 5i is a 0, then so is 3 minus 5i. Automatically. Okay? So it could have 1 real, and therefore the other 2 are imaginary. So I see the leading coefficient, I see the degree, I know what the end behavior looks like. So what are all the possibilities for what this graph could look like? Maybe it looks like this. Or maybe it looks like that, but has a hill and a dip, but doesn't matter. 1 real 0, and the other 2 are what? Imaginary? What could all 3 real look like? Like that? Or maybe like that? Where one of them is actually repeated twice? Or maybe all 3 of them are the same number and all 3 are repeated 3 times. There's kind of a lot of possibilities, right? 3 distinct real zeros, 2 distinct because 1 is repeated, or 1 distinct but really it's repeated 3 times. Or maybe only 1 and the other 2 are imaginary. So there's lots of possibilities. What's the only way of knowing for sure? Because even if I graph it and look at the graph, I can get a better idea. But sometimes, what if I was really mean? Which I'm not, right? I don't ask trick questions, ever. What if I drew a graph that just barely went below the x-axis and immediately came back up like that, but you thought it was touching and bouncing away? What if I gave you one that actually had 2 different x-intercepts? They were just super close together, like 2 and 2.1. So when you graph that thing in your calculator, you think it's touching and bouncing away, but it really isn't. That would be cruel, wouldn't it?
You would check by the amount of
right. Or even better. This one's even better. What if it looks like it touches the x-axis, but the reality is it doesn't. It's just barely above it. Ooh, that would be mean. Luckily, I don't ask trick questions. I do lie, though. So, what's the only way we can know? And solve. So set it equal to 0. What's our favorite method for solving this? Factoring. What do you notice? X can be factored out. And then that trinomial can be factored down to x minus 2, x plus 1. Now I know, beyond a shadow of a doubt, all 3 of these zeros are what? Real. Are any of them repeated? No. I know the end behavior. Could I draw a quick sketch of this? Absolutely. It's going to be crossing at -1 0, and positive 2, and it's going to be coming from negative infinity to the left and going up to positive infinity to the right. Very rough sketch. I don't actually know how high that hill is, how low that dip is. Remember how parabolas, the maximum, the vertex was halfway between the x-intercepts? Is the x-coordinate of this hill going to be halfway between these x-intercepts? No. So we really don't have a method besides our calculator for finding maximums and minimums. We will not be finding maximums and minimums by hand, well, except for parabolas. You can do that. Sine and cosine, secant, cosecant, you'll be able to do that. But we do not have a way of finding maximums and minimums by hand of this graph, not until next year when you take calculus. That's one of the big things in calculus, finding maximums and minimums. Okay, does that make sense? Good stuff. Do another one. So this problem right here says to find all of the relative extrema. Find all of the maximums and minimums, of which there could be at most how many? There could be 3, right? The degree 4. There could be, actually, because the end behavior is negative, leading coefficient, there could be 2 hills and 1 dip, right? It's a degree 4. It's an upside down degree 4. So there could be 2 hills with 1 dip in between them, at most, maybe. Let's actually solve this thing for the zeros. How do we factor that? Factor out a negative 2x squared. That leaves me with x squared minus 1, which is a difference of squares. So we get x minus 1, x plus 1. So what are the zeros? 0, 1, and negative 1. I'm going to pretend like I didn't hear what Alex just said. You heard nothing. Jedi mind trick. So how many zeros does this polynomial function have? Do we know? It's a degree 4, so it has to have 4. But I only wrote down 3 numbers. So the zeros are 0, 1, negative 1, and what's the 4th? It's 0 again. Not imaginary. How do I know that? Because what is the factor that corresponds to that 0? It's just x. That factor shows up twice. There's x again, there's x minus 1, and there's x plus 1. The factor x plus 1 corresponds to the 0, negative 1. The factor x minus 1 corresponds to the 0, 1. One of these x corresponds to 0, and the other x corresponds to the 4th 0, which is also 0 again. So, keeping in mind the end behavior and what we know about all 4 of the zeros, could you draw a rough sketch? We're going to have an x-intercept at 0, and I have to remember that that is repeated twice, an even number of times. We have an x-intercept at 1, we have one at negative 1. So it's going to come up, cross through negative 1, touch 0, bounce away, and then cross through 1 like that. 2 hills, 1 dip. Do I have any way by hand of knowing the exact location of any of those extrema? Actually, I do know the location of one of them, 0, 0, because it is not only is it an x-intercept, it's also a minimum, isn't it? But do I know how to find the locations of these maximums by hand? No, we don't.
How could it be like, even though it looks like you're 0, I mean, for sure.
If it's not, then there's no way I would have had 0 as a repeated root. I would have had either not 0 at all, and therefore the minimum was actually above the x-axis, barely. Or, if that minimum was actually below the x-axis, it would actually be crossing the x-axis at how many different points? 4. Here, here. And if that minimum was below the x-axis, it would be crossing at 2 different points, and I would have found those when I solved the equation. Does that make sense? If the minimum is actually above the x-axis, I would have only found 2 total solutions, 1 and negative 1. If it's a repeated root and it's touching and bouncing away, that is at the very bottom of that dip. Does that make sense? Great questions. Here's the book talking about repeated zeros. Okay. Anytime a factor shows up more than once in a polynomial, so let's say x minus a is a factor that shows up in the polynomial k times, then we call a zero multiplicity k. If k is odd, the graph does cross at that point, but like I said, it levels off. It becomes parallel to the x-axis, then crosses through. If k is even, it touches and bounces away. But like I said, the larger k is, the more flat it gets and runs parallel-ish to the x-axis, touches it, and then bounces away. Find all the zeros of this one. Ew. Gross. How do you find those zeros? By hand. I sure hope you don't know a formula for a degree 5.
Well,
Nasty.
I mean, like you can guess 1 0, and then is it like?
Oh, so you're talking the rational root theorem.
Yeah, rational.
Yep. We'll be going over that. I don't know if we're going over it now though. But you look at this number, and you create a list of if this. So how many zeros does this polynomial have? It has 5. At most, how many could be real? All 5. Or how many could be real? 3 and the other 2 are imaginary. Or 1 is real and the other 4 are imaginary. Do I know how many of those roots might actually be rational, which is a specific type of real number? I have no idea. Maybe none. But if this polynomial does have rational zeros, if this polynomial has rational zeros, they are either 1 or negative 1. So you can guess and check those. Just plug it in, see if it works. So that's one way you could do it, but best case scenario, you find a couple that were, well, best case scenario, 1 is repeated 5 times and goes to the Keyword there, you just said factored. Factoring only works if the equation is equal to what? You're seeing things.
They're back. They're back.
Go away.
Yeah.
Wow. That is bad enough. Nidra. I just didn't answer your question. It was very annoying. Go away. Who are you? I don't even know who you are. Okay. So for now, I would say we graph this thing. I think I'm losing my voice. Okay, and I always start with the zoom 6. If you press zoom and then press the number 6, it takes you to the standard viewing window. Do you believe this is a pretty good view of this graph? I don't really know. I mean, it looks like I see 1, 2, 3 x-intercepts, so there could be 5. So what if it actually comes back down and back up again? I'm not seeing it. Okay. Here's one thing I noticed. I think it's doing something weird here. It kind of curves out and then back in, which to me is a signal that probably is actually a good view. But what you might want to do is zoom out, make sure you are seeing the whole thing. But those look good. Where does it look like it's crossing the x-axis right here? -2, but I actually know that it in fact is not crossing -2. -2 is not allowed to be a 0, not a potential rational 0. So it's probably some weird irrational, like -2 point blah, 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 blah. So if we were to do second calc 0, the second option there, we can actually have the calculator find the 0 for us. It's going to ask you 3 questions: left bound, right bound, and guess. For left bound, you want to make sure you enter in a number that is definitely to the left of that x-intercept. So you can either move your cursor by hitting the arrow key a bunch until you are definitely to the left of that, or you can actually type in a number you know is to the left. So I'm actually going to type -3 and hit enter. Okay? Now it asks for a right bound. Make sure you don't include more than 1 0 between your left and right bounds. Does that make sense? Make sure your left bound is either below or above the x-axis, and your right bound is the opposite of that.